What happened a little faster this time? That's interesting. My iPad though. What's that? In this guy. That's funny. I was thinking about not teaching today. I'm just giving you guys a bunch of work to do.
Oh, I have a quick question.
Yes.
It might be a silly question. So for the tour, if they're taking us to the campus, are they bringing us back?
Yeah. It better be.
Yeah.
I mean, actually, there's a question to ask, and I don't know the answer to
Well,
this.
they explicitly said they're gonna bring us there, but they didn't explicitly say they're gonna take it back.
Well, you've already paid your tuition, so they got their money out of it, so they're good. But no, I suppose that's one thing. I guess you bring up kind of an interesting point in that. What are the hours of the bus? I mean, that would be something that's worth publicizing. You know, not tomorrow, but
I think they posted the bus schedules within the
did they?
yeah, there's like bus schedules, but I don't
But-
take the bus, so I just.
Well, but for other students, it would be worth knowing, like, when's the last bus?
Are they using the bus?
I think they're using that.
Or a special phone just for.
So there is a new bus route that they created last semester.
But that's what they're using today, or are they using special just for us?
No, it's you're on the regular. As far as I know, I don't think they're. I mean, because when I was with Jadine in the office, she was just looking at the bus times, like the 5 o'clock bus is actually 5:01. So apparently. They're very precise. Anybody look at Weather Underground when they look at the weather? Weather Underground, it's one of the big weather sites. I mean, if you look at the weather, I look at the weather a lot because it affects my outdoor plans. But Weather Underground, if you can set it to metric if you want, so you can do SI, of course, that we're all used to, inches or whatever. If you set it to metric, it'll say something like 3.8 millimeter, 3.84 millimeters of rain, or 3.84 or something, like 3.84 millimeters of rain. Really?
Not like.
Yeah, we have this down to, 10,000 to 100,000 of a meter. I'm sure you do. I assume it's a unit conversion thing that they did, and we never did any rounding on, which is a little bit silly, but anyway. So assuming the bus arrives at 5:01, to me, that seems pretty precise. I would say plus or minus 5 minutes. I don't know, how reliable is the bus service on that? Anybody use it?
I don't know about the purple one, but the 12 and 114 on Collins is pretty reliable.
Is that the Capital District bus, CDTA bus?
Is the purple not a CDTA bus?
Purple bus is Albany bus. So it's dedicated for Albany. I think it's still CDTA, but it's, is it,
No.
It's like the 801, right?
there's like that kind of, what is it, two trailer bus or whatever it's called.
The accordion bus?
Yeah,
Oh,
I don't think that's what it's called, but yeah, it's a good description.
CDTA, but like because it's for Albany, it's express, so it costs more than it takes to take the 12 bus.
Well, that's
Like
what
if
it
you
is with
were
the 11th
favorite.
year.
But you don't,
It's free for students, yeah.
you have to pay to get on the bus?
No,
It's free for
for
students.
students it's free.
Oh,
For students if you get through card, but like for
I mean, the E11 is also just for like, it's just, that just goes between uptown and downtown campus, right?
but the 11 they discontinued.
Oh, they
Because
did?
yeah, because they made the 910.
Oh,
So
that's
910 is
annoying.
more expensive.
I'm
because
learning
it's
bus
made for
numbers that I never knew about.
schools.
I like the 11.
I've never been on the bus. Actually, I've never been on the bus in New York.
Oh, really? You should try it for somebody.
I was getting into a bunch of Twitter arguments earlier about the buses in the city.
In New York City?
Yeah.
Trying to think if I've ever been on the bus in New York City. Certainly been on the subway.
I mean, if you're in Manhattan, you don't really need to be taking any buses, but every other borough you kind of do. Manhattan is just drenched in subways.
Yes. I will be there on Saturday,
I also will actually.
going to the city. Taking the train. Love taking the train to New York City. Anyway. So. Questions, I mean, nothing. So there was the long prep assignment, I hope everybody did it. No,
No, I did what I could.
you could have stopped by and asked.
No,
I mean, that was kind of the hope that you would look at it and
no,
ask them.
asking.
Yeah, ask me now. So the prep assignment was kind of a small. I don't know, review assignment to things that you should be able to do for the exam. What else? We do have homework due tomorrow. It is what I would consider a fairly short homework. And I think in the homework I indicated we had studied a similar problem previously, not the exact same. So this is, but this, the homework problem that's due tomorrow, this coaxial cable problem, this is a real problem. I mean, this is a real geometry. We can go get coax cables, cabinet there. It has these exact type of characteristics, so I don't know if I put the numbers, maybe I didn't use numbers, but. But coaxial, that is one of the most real problems that we could look at. And if you like look at a class like microwave engineering, I don't know if anybody's registering for that. But coaxial cable characteristics would come into play in that class. So you would study things like propagation velocity, and propagation velocity relates to the inductance per meter of the line and the capacitance per meter of the line. I don't remember if we did that exactly. Coaxial geometry for capacitance. But the impedance, also coaxial cables have impedance, and that relates to the inductance and the capacitance per unit meter as well. So the geometry we're talking about there is significant. It's also true of microstrip line, but microstrip line tends to be fairly short. So when I did kind of describe microstrip line, it's coaxial cables can be very long, sort of very significant in the power industry, and historically very significant in communications via Time Warner back in the early days of getting cable to your house or Spectrum or whatever the provider is. It was done with coax to your house. The backbone was done with fiber optics, which is actually something we will touch on a little bit in this class. Concepts there that apply to fiber optics. We'll look at in terms of plane wave propagation. Anybody have fiber to the home? Anybody know if they have fiber to the home? There was a big push starting about 10 or 15 years ago to get rid of coaxial cables and just fiber all the way from provider all the way to your house. In your house, you might still have coax. So nowadays you probably have wireless.
What's the trade-off? Because they're all used.
So the issue with coax is it's lossy. So they had there's an amplifier, I think roughly every couple of kilometers or every kilometer or something like that. So they run the coax down, wherever you live, Troy, Albany, or whatever, and then they have to have amplifier. So they have to amplify the circuit.
Trade-off with fiber.
Fiber, you don't, you have much longer propagation. So there's still some attenuation, but it can be many kilometers.
But it's only better.
Yeah, it's better.
Only better. Nothing else.
I mean, from a manufacturing point of view, I don't know if it's more expensive or not. I mean, I guess off the top of my head, I would say it's maybe a little bit more exotic in materials, but I don't know with today's manufacturing, if it actually is more expensive. I mean, early on, I
I think
assume
with fiber from physics, you can only bend it so far before it loses.
that's true, coax too. So we can, go take a coaxial spool and bend it pretty hard. I mean, we can do a U shape, but if you kink it, then you'll get reflections off that, but fiber will snap. I mean, fiber will actually break, coax will deform, which could be. You could still maybe get signal through, but it would be problematic, so.
A little bit of a trade-off. Because the coaxial cable on our house, like we were house around the corners.
Well, but I mean, some of the fiber is pretty flexible. Yeah. Oh, so So the backbone fiber, so like the stuff that runs, miles and miles and miles, it's big thick stuff and yeah. I don't know how they protect it from earth movements or something. It could be in a kind of enclosed area or something like that. But yeah, I think that stuff is, not very flexible. But I mean, you can go. Like if you've seen any of these like fancy little things where, shine LED and at the other end glows, that stuff's really flexible. And that's all you need in your house. You don't need a big, thick. So it's fairly cheap line and. I mean, I don't know exactly what the material properties are, but I think the flexibility would be comparable to a coax, maybe even better. I mean, I'm not sure you would want to wrap it around something. Or take hard right angles, but you don't really want to do that with coax either.
I want to make sure, but Tuesday you said the test was next week. That means Tuesday, right?
Yes, we have the Tuesday. Is that
Okay,
not right on the calendar?
I didn't check the calendar. I have the calendar in my
It
head.
is right on the calendar. So yes, our test is in 5 days.
For the prep assignment, be able to do a solution on that.
Sure. Which one are we looking at? All of them?
Yeah,
First
do a
one.
whole thing and post it. I'll do it right now.
Oh, I can do it right now. I mean, today we can open up. I don't remember what was on the calendar, but one of the days I just have magnetostatics review, so that's what it was for. Oh, that's weird. Well, apparently Firefox is not behaving. The hell?
I like you to.
Well, other than quirks like what just happened, I'm happy with it. I mean, it's really light. You could throw like a frisbee. It weighs like, well, it's not something I normally do, but we have homework due tomorrow.
Yeah, but it's like the magnetic energy density and all that stuff.
Oops, I didn't mean to bring up anybody's specific answer. I mean, so this is just a coordinate transformation problem, so. Kind of looking at this, let me write it down so I don't forget. So current carrying wire, carrying current, 2 different wires, current carrying in the X direction, 2 amps on the X axis. And current going in the plus X direction, and then the second wire on the Z axis, current going in the minus Z direction. So first, I guess first question, what type of problem is it? What type of problem is it? It was in the problem definition. The superposition, we have a contribution from one current distribution and a contribution from another current distribution, and they add, so we can look at them separately. And this was designed to like go just dig into your notes. So what is the field? What's H for a wire? We've done this problem. I didn't expect you to re-derive it, though you should know how to derive it, but what's H for a current carrying wire? I mean, you can dig through your notes. What is it? I'm asking you. I'm not going to tell you. Yeah. If he had in cylindrical coordinates, So there's a coordinate element here. So you do need to know how it behaves. You need to transform from cylindrical coordinates. There's a coordinate element here. Back to Cartesian. So, but we can for H1. What's our field? Or I'm gonna back up a step. I mean, what's I for H1? 2. And we have 2 pi. What's R for H1? Yeah. So we don't care about the X component. So if we look, there's X coming out. So I have to think of my coordinate directions here. There's Y and Z with X coming out. And we're at 0.2, what was it? 2, 3. I mean 1, 2, 3, but we're 2 elements away. 1 out of the page, but 1 out of the page doesn't matter. So there's our R. So a little bit mathy. R equals 2 squared plus 3 squared. So square root of 13, I guess, whatever that number is. And we can't leave it as phi hat, but what's the direction? We can figure that out. So phi hat is a unit vector, but if we want to translate to Cartesian coordinates, what's the direction? What is the direction?
Like that.
Not quite. So looking at this, how would we draw our field lines? So current is coming out of the page upward. So we would look at circles. Let's change. So right-hand rule gives us circles around our current carrying wire. And then we have to find the unit vector on that part of the circle. The tangent unit vector. You have trouble.
Yeah.
Which part?
Guess the direction. That was it's the tangent.
To shift from X and Y. So I mean, we can use coordinate transformations or whatever. You can look it up, use a tool of going from the phi hat direction in this case to the X and Y just to collect in the Cartesian. X, Y, and Z. Is that? Or sorry, Y and Z. So we would have a Y component and a Z component. What did I say? X and Y. Y and Z.
Oh, so it would be transforming the phi into a Z and Y component.
Yes.
Oh, okay.
I mean, there's some trigonometry associated with. We could find this angle and just find the components, the component in the positive Z direction, the component in this case in the negative Y direction. So there's some trigonometry there. And then H2 is 1. And there's that 2 pi. And we're on the Z axis. So we can look at it again. Here's coming out of the page. We're now looking at the XY plane. Actually, we're looking in the negative Z axis. So I can flip these guys just to be a little bit more complete. X and Y. And we're still at some point 1, 2. So R1, R2, 1 squared plus 2 squared. And if we want, I mean, we can crunch that as a number if we want, square root of 5. And it's in, again, we can translate, so we're looking at, there's our circle traced by our field line. And again, translating to, oops, or x and x. Oh, that's not good. You can translate to the x and y coordinates. So a little bit of annoying trigonometry, I won't disagree. I suppose I could have made it easier from a trigonometric point of view. And then the field at that point is the sum of H1 and H2. Do we agree? Yeah.
Can you repeat, what's the direction of the field line?
So the cylindrical direction is the circle going around. But you have to find the tangent to the circle at that point. So a trigonometry problem. I mean, in the same way that we found the radius. So. Yeah.
How would that be written down? How do we write down the, say for the first one, the z and y components? If we were gonna do the trigonometry, how would it be written down? Like how would we show that?
I don't quite understand your question. So, I mean, ultimately, we want a unit vector because phi hat is a unit vector. We can, I mean, you can decompose this into the vector components. Is that? So we're looking at that unit vector, right?
Yeah,
Is that?
and then is it? How would we do that? I guess that's the base question.
I mean, it's, so if we do this. That's a 90-degree angle. And so, I mean, there's a couple ways. This is just what's coming off the top of my head. You can do this math and find that vector and convert that to a, because you know this, you can find that, that's tangent minus 1 of whatever, and then this is 180 minus 90 minus that. And you could find the vector of that angle. That's one way of doing it. I mean, once you know this angle, so that's some phi, and so I shouldn't use phi. Let's use theta. And so the unit vector that's pointing in this direction is cosine theta, if this is x and y. I mean, we have to look at the coordinates that we drew, but cosine theta x hat plus sine theta y hat. I mean, there's probably other ways of getting that vector, but
Oh, okay. There you go. I see it.
actually, more technically, I should be a little careful. Should use that, call that theta. Just to make sure my signs come up right, because otherwise I should have put a minus sign. So trigonometry problem. Again, I guess I should have made it easier from a trigonometric point of view, but. Or you could just go online and convert a point to a unit vector, find some conversion tool. Which I'm not against because I don't really care about the trigonometry. I care about the fact that this is a superposition problem. And the field is I over 2 pi r. That's the field's question part of it. Getting hung up on the trigonometry is easy to do. Yeah,
What do we look for when we're using that equation?
what's that?
What do we look for?
What do you mean look for? I'm converting the cylindrical to Cartesian. Cylindrical phi hat. Do we use, no, I just forgot. Do we use phi hat or theta in cylindrical? We've been using theta? Phi, we did use phi, okay. To x hat, y hat, z hat. And it's only two of those in Cartesian. But I included all of them because one of them will be zero per wire. Overall, we get a contribution from both. Again, this is way beyond the scope. I'm not gonna ask you to do this on the test. I mean, it's fine if you want to talk about it, but doing trigonometry on the test is a waste of time. It's not a Fields question, it's a trigonometry question. Giving it to you as kind of a homework problem is okay with me, but giving it to you as a test problem is just a tedious time sink. I mean, it's, I suppose, good to remember the trigonometry, but I have to think about it for a second myself. But as I said, recognizing superposition and then recognizing kind of these two things are what I cared about, mostly in converting. Just cylinder or a Cartesian was more a chore than anything else. All right. Now, what was our other ones? Well, hopefully this one was straightforward enough. I mean, if I have current here, where this was 1 centimeter, and I have a JS coming out of this guy. I mean, those aren't wires. I need to make a comment about that. J goes to some J naught amps per meter. I guess it was in some direction, it doesn't matter, X hat. Where J naught was 1.5 amps per meter. Was total current. It was not. That was supposed to be a much quicker problem. Yeah. So I equals J naught times, this is a weird way of saying this, but cross-sectional length. Which was 1.5, 0.01. That's several, you said 15 milliamps total current.
Oh, it wasn't J.ds.
I mean, it's always J.ds, but it's a surface integral. We had that conversation on Tuesday. If it's a surface integral, we don't do J.ds. Same with wires. If it's wires, we don't do J.ds. I mean, it's always mathematically J.ds comes out of Maxwell's equations. That's always the fundamental vector expression for total current. But if it's these other things, we don't have to do the vector calculus. We can, I mean, I've said this before, I can write it out using delta functions. And I can represent J.ds mathematically, but I don't want to, because we don't need to.
I thought for this question, when you said a sheet of current, I thought it was like a
Some
piece of paper,
thickness.
a piece of paper with a length and height of 1 centimeter.
Oh, you thought it was coming out of the paper?
Yeah, so I did 1.5
Well,
times that.
but this, so, I mean, assuming I don't screw up, there's the surface current clue right there. Because if we're representing the current density as amps per meter, it's a surface current. Which means it's infinitely thin. So for what you're saying, if we had something along the lines of, you know, if this was X and Y, and we had some current here, then this would be some J equals whatever J of X, Y is. Z hat. From I realize I've said we need to use units more, but I do try to write them down when I'm expressing our current densities, and so that's amps per meter squared. So total current, when we do J dot DS, DS in that has units meters, meters. So amps per meter squared times meters, meters is amps. Does that make sense?
Yeah. Yeah, get that one.
I still Well, no, I mean,
I thought of it like as a sheet like that, but I got the same answer in J.DS.
I'm not sure how. So I mean,
Like,
I
the area
did
of
be
the
straight up.
sheet is just like its length or whatever squared, so
So you
whatever.
did
the length
1,
was,
1?
I just squared it and times it by 1.5.
Yeah, but 1 centimeter squared is 0.0001. Yeah, that would be 0.0001. And then you would get 0.15 milliamps. No, I don't. I mean, if it was a 1 centimeter square wire, the surface area is 0.1 meter squared. There, sorry, 0.0001 meters. Anyway, is it clear now?
Yeah.
And then the next thing, I mean, it's kind of the same procedure except in reverse, so. This is what I said earlier, a few minutes ago, and talked about earlier, this is microstrip line, so. I've drawn this out before, we have a second parallel current sheet. With a smaller cross-sectional area, this is very real. So. I mean, maybe not this specific geometry, but where we have some. Here again. 1 centimeter. All right, the dimensions may not be real, but good enough. And we have current once again coming out of this. And those are current density lines, not wires. And then we have a parallel, parallel smaller one with a higher current density. Oops, that should be X's going in the opposite direction. So from a visualization point of view, it actually looks something like this. An isometric point of view is what I should be saying. Didn't quite draw that as well as I could have. But dot, 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 dot. So it's a strip of, when you think about the table, some thickness above it. And then there's my opposite directed current flowing in the ruler going the other direction where the ruler is infinitely thin. Arguably infinitely thin. That's the geometry. And so in this case, what's our current density? J L, I suppose, for line current was 0.015 over 0.002 and 7.5 amps per meter. So a larger current density because it's a cross-sectional length is 1/5. I mean, that would be a quicker way of figuring out. It's 1/5 the length, so it has to have 5 times the current density. 1/5 the cross-sectional length. You fall asleep? Okay. You can fall asleep.
Why are they divided?
Oh, because this was total current. I'm trying to find current density, so I left off some of the things I could have. This is I over X sectional length equals amps. My cross-sectional length is in meters. So this was total current. So I'm going the reverse way. Here I'm taking surface current density times my cross-sectional length to find the total current. For the second part of the problem, I wanted to find my surface current density, which is I divided by my cross-sectional.
Oh, okay.
It's good?
Think we minus two.
Yeah, you're right. I should include the negative sign because the polarity is in the other direction. You're right. It's a good point. Everybody agree? So this is both a current density. Again, I use this term loosely, a volume current density. And at for R less than 2 millimeters, and then a surface current density at R equals 4 millimeters. So what's the total current? So if we look at our geometry, I mean, we can look at it from two different orientations. There's our 2 millimeters. And there's our 4 millimeters. Inside here, we have some current going around in circles, which is not very realistic. And then here on this surface, we have current going in the opposite direction. So it's a surface current. The other viewpoint, so this is looking along, looking in the Z direction, I suppose. Alternatively, we can look at it like this, which we've done before. And then right through the center, we have current. I'm just going to think for a second. What do I want? Coming out of the page on this side and going into the page on this side. Though close to the axis, the current is 0. So that's not very accurately drawn dots and X's. There's R equals 0. This is R equals 2 millimeters. And then likewise, a surface current at R equals 4 millimeters. Reminding ourselves that this is slicing our cylindrical geometry lengthwise. So it's just a mirror image on either side. We don't really need both sides, but I just did it for completeness. And here we have current going in the opposite direction and current coming out. So what are we looking at? We're looking at a per unit meter length. So this is 1 meter. And we're asking how much current is coming out of it. So we can look, our surface current we've already done. Were they the same directions? I mean, I suppose in some sense it doesn't matter, but you're right. I mean, whether it was opposite or the same, it's just a difference of a minus sign, but we'll run with the opposite because that's what I drew and I don't feel like undrawing it. But so we have from the surface current, we've already done this problem. The total current is J length times X sectional area, cross-sectional length. To use the same phrasing. And so it was 2,000. That's a lot of current. Is that really what I wrote? Okay. Yeah. That's funny. Probably not what I meant to write, but oh well. Times 1 meter is 2,000 amps. Yeah, that's cute. Apparently the other one is negligible. Why, I wonder what I was thinking. Yeah. Doesn't matter. But the more interesting one, I suppose, is this region. What I tend to call, even though it's not a very good name, the volume current does do what we talked about. We have to do integral j.ds. Which winds up being J was, oops, where are we? 500 R? No. 500 R. And what's our DS? I suppose I should ask that. What's our DS? What is our DS? DRDZ. Very good. DRDZ. And 0 to 0 0.002 and 0 to 1. There's our unit length. So that was the unit length. This is infinite in cylindrical scope. So plus or minus infinity as far as Z goes. Per unit length is along the Z axis. And I suppose this number, as was already mentioned, is much, much smaller. 500 times 0 0.002 squared over 2. And I don't know what that is, but what's that? 0.001. Okay. I suppose I should be able to do it in my head. Well, 500 times 0.002 is 1, but then we have the 0.002 again. Yeah, I agree, 001. So total current 2000 plus or minus 0.001. Minus sign anyway, so suppose I should have paid more attention. Anyway, that same, I mean, I put this up because we've had a lot of discussions about surface currents and how to calculate them, and it's always been a challenge. And there's no real calculation. It's the current density times whatever that cross-sectional length is. There's no more to it. I should add a side comment on a similar note. When I graded your Tuesday prep assignments, everybody used current density. The problem was given in winding density and amps. So current per wire. So I don't know where everybody got a J naught. I suppose that was because you used the video instead of going back and looking at our discussion of wires instead of surface current, but it was not a surface current problem on Tuesday. So if you look at I did post those grades, I think. So if you looked at that, you'll notice. But the current, I mean, I've said this before, and I can write it down formally if you want, but we can define a surface. And if it's a winding density problem, the total current through that surface is whatever the length of that surface is, times the winding density times the current. I mean, we can do it formally. We've done it. It's in our notes already somewhere. But if I have, again, these are now wires. And I can have more. N windings per unit length. Whatever that is. So usually 1. So, 2000 wires per meter. That's probably not a totally unrealistic number of wires per meter. I'm gonna think of that. Each wire is 0.5 millimeter. It's densely wrapped. Yeah, all right. Or 2 layers or something like that. 1 millimeter radius wires. Probably not unrealistic. If I define a surface, my surface can be all the way out here. Doesn't matter where it is. Then this length I need, there's my length. Whatever that is. And so I total is N per unit length whatever that is, times length. These are not necessarily the same thing. I mean, this, like I wrote here, 2,000 wires per meter, if that's a centimeter, then we have to account for that. Times I per wire. They all have the same current. That's an important thing to qualify, that when I wrap something, as you did with the toroid or the solenoid in class on Tuesday, in lab on Tuesday, everything has the same current. Now, I should be a little careful, and there's some realistic issues here, that if we crank up the frequency, it turns out that there are wavelength limitations, because as we learned in physics too, there's a relationship between frequency, wavelength, and speed of light specifically. And so if we're looking at AC problems, there is a speed of light associated with how the wave propagates in the wire. And so there is a real physical distribution of how the current behaves as a function of position on a wire or a sinusoidal signal. If our wire is relatively short, we ignore that. We assume that everything has the same current. But as we make things longer, and this goes into microwave engineering, so again, I've said this already today, this class you're interested in, then this wave as a function of position as well as a function of time, which we will touch on in this class when we start playing with materials in a couple weeks, is a real thing. It matters a lot. Actually, it became a huge thing in computers. So transmission line theory, which is the same way thing kind of as plane wave theory, very similar. Transmission line theory is transmission lines, you're transmitting stuff. So the power system is a transmission line. And it was a huge deal back in the 20s and 30s and whatever 40s when we were first electrifying the country. How do we transmit power? Because power is sinusoidal, 60 hertz. And then it died. There are still people working on it, but no one is hiring transmission line engineers anymore until computer clock speeds got so high that the interconnects between things in our computer were transmission lines, and how the voltage and current varied as a function of position on those interconnects became significant. And we have 2 gigahertz clock speeds now. And if we look at the speed of light, which is capped at 300 meters per second, then our wavelength is much less than a meter. If you remember that from physics 2. So we can make things easy and say, all right, we're running our computer at 3 gigahertz. It means our wavelength is 1/10 of a meter. If we're operating at the speed of light, which is not necessarily the case, could be operating at a lower speed. But 1/10 of a meter, 10 centimeters, if the interconnect between your hard drive and your motherboard was 10 centimeters, which it frequently was back in the early days of computers, you have a transmission line problem. So that's a little side note that worth talking about, because I think it's kind of a driving force behind RF circuit design. If anybody is interested in going in that route, I just had a conversation with Dr. Saunier about that before class started. Back to our discussion here. When we're looking at a wire problem, we want to look at the winding density and the current in those wires. The whole driving force of that conversation we just have is we need to know that current, of course, and that's why I write I wire. So if we have 2,000 wires, and if length is, 2 centimeters in that direction, we have some width here, but the width doesn't matter. I don't care, because it's not an integral J.ds problem. It is an integral J.ds problem, but we reduce it to something similar. And I wire is, we'll just throw out some silly numbers here, half an amp, 0.5. Then I total per in our 1 centimeter thing is 2,000 wires per meter. I suppose I should really spend more time with units. 0.02 meters times 0.5 amps. Amps per wire, just to cross things out. Cancel, 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 cancel. That was a meter. And we get 20 amps, I suppose. 20 amps total, not 20 amps per wire. So we'd have 20 amps. Flowing wrapped around in a 1 centimeter, so if we took our solenoid. Wrapped it around 2,000 times over 2 centimeters, or not very, or sorry, whatever. Not 2,000 times, whatever number of times that comes up to be. Then we would have 20 total amps flowing through. The surface that intersects with our solenoid. So you did not run half an amp through your wire. Probably ran a few milliamps. That's something else, I suppose, that is from a practical point of view worth knowing. So we use copper. Anybody have any guess over what? That wire could handle? Anybody know where they would find? Yeah.
I'm gonna guess 20 amps.
Anybody know where you would find that information? Seeing as every one of you has already looked at it at least once.
The internet?
Internet, but let's be more specific. The internet's a great place to look stuff up. You've already looked it up. You didn't pay attention to it, but. Where would you look it up? Something that I've had you look up before in this class. Where have you used the internet in this class? The AWG table. So it has for copper and aluminum, it has different, usually it's copper and aluminum. It tells you what the wire, the current rating is for that wire. And it's, for this one, it's probably down around an amp. I would guess. What do we use? 28 gauge wire? Maybe 26. Yeah. I'm gonna guess it's around an amp. 20 may be a little high. So what happens if you go too high? You can't burn wire out. The wire is an ohmic thing, and you can turn it into charcoal. And if we want 20 amps, what do? We go with the lower gauge wire, and that's in the table. So you can find lots of references for this. So the internet itself is a general answer, but you're looking essentially at the American wire gauge table. And again, the two principal ones in the American wire gauge are copper and aluminum, and they do have different conductivity, so they do have different ratings for allowed current. So these are things worth knowing if you're gonna ever do anything with power. In my office, I've said this before, you can stop by and look, I have a bunch of motors that are bigger, and I have, gauge wire that's probably, I don't know, 8 or 9, 10 gauge wire or something that's wrapped around those motors, with much thicker wire. Designed to higher, much higher currents. I think that was it for the prep sign. Was there another problem? I think that was it.
I don't know why I ignored the end.
You, no one, everybody did J-Dot, the whole class. Except for a couple of people who put 0. I don't remember who that was. I'm not sure why people put 0, but. I suppose when all else fails, put 0 or infinity, those were guesses. Or 1. Yeah, no, not a single person did, and
It looks like
maybe
there's
one
something
did. No, you
over
did. Everybody else was J-Knot. Was it a big group collective that said, let's just use Superskirt? So somehow unconscious connectivity between everybody. Are you awake? So again, kind of an open day if you need it. I can always go faster. I mean, one thing that did come up before class, so I gave you a problem on the homework that we didn't fully touch on, but it's fully defined, so you don't need more information per se, but we can look at energy. And so in physics 2, for an inductor, we can look at energy. Energy is W, and it's magnetic energy, and magnetic energy is 1/2 Li squared. So in physics 2, I hope you saw that at some point. Never really said it in class, but that's the energy that's stored in an inductor. For a capacitor, we can look at the same thing.
it's electric energy, so we have a subscript E there, and it's 1/2 CV squared. And if you go back and dig through your physics 2 notes, or I suppose, find the appropriate reference on the internet, you will find those equations. I mean, those are the equations associated with how much energy is stored in the capacitor or the inductor. And those are kind of boxable equations if you want. Those are defined equations, yeah.
What's the subscript, M and E?
M for magnetic, E for electric. So we're storing magnetic energy in an inductor. And we're storing electric energy in the capacitor. So, I mean, it goes to what's our geometry. In an inductor, we have current flowing, and if we have current flowing, we have field, right? And so, the energy is stored in the field, which is where we're going with this. Likewise, for a capacitor, what do we have? We have a voltage difference between the plates. But if we have a voltage difference, we have an electric field between the plates. Right? If we have a voltage difference, gradient of voltage is electric field. So in a capacitor, the energy is stored in the electric field. So we write it as 1/2 CV squared. That's kind of the macroscopic circuit viewpoint from it, though we never really looked at energy in circuits. I mean, maybe I brought it up, but I doubt it. But ultimately, to follow up on your question, for an inductor, the energy is stored in the magnetic field. No magnetic field, no energy. Ultimately, we can write it as 1/2 Li squared. And I suppose for completing this down here, we can write the energy is stored magnetic field in the electric field. So energy stored in the magnetic field, energy stored in the the electric field. For magnetic energy, we can define a concept lowercase w. So that's supposed to be capital W, lowercase w is 1/2 B dot H. There's a lot of significance with that energy density equation, especially if B and H are not parallel. For our purposes, they are. So, but once you saturate, we talked about this a little bit, we looked at hysteresis briefly. If you take an iron material, there is a maximum field that you can get into it before it saturates. I suppose if you want to think about it, not dissimilar to an op-amp saturating. There's a maximum field, and at that point, the energy density becomes more problematic. For our purposes, we're letting B equal mu H, so B is parallel to H, and this eventually can be written as 1/2 mu times magnitude of H squared. That's just using B equals mu H, and H dot H is magnitude of H squared. So dot product is a scalar result. This is energy density. Joules per cubic meter. It is a volumetric expression. Energy joules, and its density in a volume sense. So joules per cubic meter. Field exists in a volume. We don't have surface field. I suppose there are some things that kind of look at surface elements with regard to field way beyond the scope of our class. Total energy then is capital integral lowercase WM dV, volume integral. So some triple integral, what our volume is, 1/2 mu magnitude of H squared, or we can write it 1/2 B dot H, however we want. We can do the same thing for electric energy in a capacitor. We can represent it as 1/2 epsilon E squared. Wait on that for a second. So very comparable, dV. So you integrate over the region where field exists. Solenoid, this problem is easy. Why is this problem easy for a solenoid? Why is this problem easy for a solenoid?
Cylinders are easy.
Okay. Not quite what I was looking for, but we have a wire wrap solenoid. Make this a cylinder, as you said. So Z, some radius A. And some winding density. Ugh. And windings per meter. Carrying current on. So what's H? We can go through all the trouble of finding H, but H is Ni. Z hat. So one of the things we talked about solenoids before is the field inside a solenoid is uniform. Doesn't matter how big the solenoid is, something that gets internalized. I mean, certainly you can prove that by joining the Ampere circuits. We did it a while ago. I'm not gonna do it again. It was energy discussion. So there's my H. It's a uniform field inside the solenoid. When I look at a solenoid again, we have this issue, the solenoid is infinitely long, so arguably it's infinite in energy. So we do look at an energy per unit length. In 1 meter of solenoid, what's my energy? What is my energy? It's a quick calculation. We can go do the integral expression, which you have to do for the homework. I can't say that for the coaxial cable, the problem is not quite as simple as this, because the field is not uniform, but we want to find the energy. I gave you H. We can do integral of 1/2 U H squared, but we don't have to do the volume integral. Why don't we have to do the volume integral? This is something to recognize. It has nothing to do with fields. If it's uniform, if it's constant, what's the easier thing to do? I mean, I have no problem with you doing this on the test, yeah. We're close. Multiply by the volume. If it's uniform, you can do the integral to get the result, because the integral of the constant gives you the volume times that constant. So this is energy per unit length. We need to be careful a little bit. Per meter, in essence, is 1/2 Ni squared times pi a times 1 meter. There's my unit length per meter. Per unit length. Oh, thank you. I didn't write that down. Yes. What's that? Pi a squared is the cross-sectional area and then the length, so
No.
pi a squared, oh, pi a squared, I said a squared and I didn't write it down. Pi a squared times 1 is the volume of 1 meter of cylinder. So. Hey. Yeah, pi a squared. Sometimes I seem to drop those squares. I like to say them in that way. Do we all agree? You confirming that you agree?
Yeah, I'm just doing the math in my head just to check. Double
The
check.
integration.
Yeah,
I mean, it comes out of. I can write it out down quickly. It's out of triple integral 1/2 mu ni squared. There's the 1/2 mu h squared. RDR d phi dz. The r comes within from the d phi component. The dz is 0 to 1 meter. There's our unit length. The phi, of course, 0 to 2 pi, a full circle, and our radius from 0 to a. Oh, and there should be oh, there's the 1/2. And hopefully, assuming I wrote everything down correctly, as far as RDR and TDZ is concerned, 1/2 mu ni squared, and I parentheses squared is a constant, bring that out front. And then this is integration that gives us the volume of cylinder, which probably you did at some point. Yeah.
I have my impression, so you know how like when we were doing electrostatics, like if we had a region R was less than A, we would observe R instead of A. Why is it that like this one, we're always doing 0 to A?
Oh, we're getting everything. This is getting a total.
Oh.
So this is, and same thing was true for flux. So if we want to look at this from the other point of view, we now have, and that was what part of the problem is. This is a different problem. But there's our HZ. So we can put a little subscript there. We have the Z hat there. But I can define B is mu H, which in this case is mu and I. So fairly straightforward, we can get the B field. But if we want the flux for one link, flux for one loop, then that's in, this is going to matter to us going forward, so it's worth looking at. That's B dot ds. And what is our ds? Let's go with a different color. There's our surface perpendicular to B. ds perpendicular to B. That's what we want for ds. When we're getting flux, we want a surface perpendicular to the B field. We're asking how much flux is going through that. Another way of looking at it is to say one loop of wire, that defines our area. I mean, that's the circumference of our loop, or circumference of our circle that's perpendicular to B in this case. Everyone agree with that? Does everyone agree? So that said, this becomes 1/2 or mu ni. ds is RDR d phi z hat. There's a z hat. I left off my z hat up there. Dot RDR d phi. There's our surface. It's perpendicular to flux. It's a circle. Z is going that. So that, oh, let's give ourselves the z hat direction. And then we're integrating from 0 to A. And 0 to 2 pi. And so once again, we can go through all that and we get mu and I pi a squared. So there's our flux for one loop. Total flux for one loop. Let's remind ourselves when we find inductance, we're looking at total flux linked. Per unit length. When we're working with wires. And so we get mu and I pi a squared. There's one loop times n slash 1, n over 1. So winding density of n windings per meter. So we just multiply it by n. So we get n squared. And that ultimately gives us inductance because inductance is total flux linked over I. And we have our mu n squared, I pi a squared in this case, over I cancels. I feel like I left something off. No. Pi a squared. And just let me, one more second. Wm, I just wrote, was 1/2 Li squared. And so we can write 1/2 mu n squared pi a squared times I squared. And if we go back and look at our expression, it's consistent with what we just did a minute ago in terms of our results. So it's exactly what we got for the energy using the energy equation. Yeah.
So that capital thing for flux, that's total flux for linkage only or total flux again?
This guy here?
Yeah, because before you said it was total flux.
Yeah, it's,
Flux.
I always struggle on which words to use here. So the psi is the flux link through one loop of wire. The capital lambda is total flux linked over 1 meter. So it's the per unit length. On the other hand, if we're looking at something like a toroid where we don't have to worry about per unit meter, we can just do total flux length because we know how many number of windings around the toroid is finite. It's whatever you did in lab on Tuesday. You wound it 25 times or whatever. And so that would be the number you would use. I mean, there's a little bit other math in that case, but. So when we're looking at a solenoid, we're interested in the winding density, which is windings per meter. So we use that per meter concept when we're doing total flux length. So there are, like, I don't know if you talked to Basit, right? That's it. So he's doing a linkage experiment with loops. So he's coupling power. So anybody who's been in his lab when he's doing stuff. And that links, that's a mutual inductance problem. We'll actually kind of look at that on Tuesday. So it's how transformers work. He's building a really shitty transformer. That's what he's got. So we have multiple, or if we have two loops, I think I probably brought this up before. You know, the old TV antennas that had the gravity ears that did this, but a lot of them also have a dipole antenna or a magnetic dipole antenna that did this. So you could see both, but it was one loop. So I think I have seen old TV antennas where they had like 3 loops, and so you would be linking 3 times the coupling, and that's something that he's working on or looked at in his lab. Is if you wound it more than once, then you're linking arguably twice as much field. So we count the number of windings that we have for a solenoid, arguably because it's infinite. we look at a finite representation, which would be windings per meter. In the lab, we did a finite solenoid, so we could have just worked with the finite solenoid geometry, which essentially you did. Does that make sense? A bit. So the more loops we have, the more flux we couple, which is why we have this total flux. Total flux for one loop is just that integral expression, and then the total flux length is just multiplying by the number of loops. And it really is, I mean, I know we did some stuff in the homework where I didn't have loops, but it usually is a loop-based problem. Where we're wrapping wires around something. It's usually what we're talking about. All right. Now, what time? This class ends at 1:20. God. Such a challenge.